Good afternoon, everyone. Welcome to the design of reinforcement piece structures problem solving session. Today is the week 5 of our in the online course. In week 5, you would have studied the design for shear and shear reinforcement, stirrups, and all those. All those lectures are going in week 5. So for that, we will be today discussing some basic concepts regarding the shear in our beams, and also we will be solving one design problem for the design of shear stirrups. So let me start. First, I want to give you a brief idea about what happens to our beam when it's subjected to loading, how shear stresses come in our beam, and how these are responsible for cracking and cracking of our beam. So let me make you a little bit understand about that. For example, if we have a simply supported beam like this, we have a simply supported beam like this. It is subjected to some loading. Let's take uniformly distributed load W kilonewton per meter. Okay, so this will be the neutral plane of this simply supported beam. If we cut and let's take a section here, we want to examine the stresses at this section and particularly at this point below the neutral axis. Below the neutral axis, we all know there will be tension. Let's cut the free body diagram and see all the internal forces within this point. So when I take this, I will make this as a enlarged one. So this will be the neutral plane of our beam section. This will be the loading coming up to this point because we cut the section XX like this. So if this would be the gross depth of this section D, complete depth, and this I said we are already seeing it at this point, small, below the neutral axis. So let me make this as this one. We are seeing it as this. So let this be at a distance of y from the neutral axis. So if I see the forces coming here, first will be the shear force at this section like this one, and the bending moment coming like this one. Okay, bending moment will be coming like this, and here will be the support reaction already because it's at the support. You can see at the above point here, it's the support. So the support reaction will be coming like this, and we have a beam section like this already. Beam section, I already told you, it will be like this depth D and width P. So looking at this whole beam section, we can write our flexural stresses distribution from pure bending equation. That like that, we have flexural stresses at the top maximum, and at bottom it will be maximum, and to the neutral axis these linearly vary and come to the 0 point, and up to this is linearly vary and come to the 0 point. Since our top will be in compression, it will be here. It will be the top compression, and bottom it will be in tension. Same will be the case now from shear stresses. If we look at the shear stresses distribution at this section, we will get like something this parabolic variation with maximum at the neutral surface. Sorry, we will get maximum at the neutral surface. If I extend this neutral surface like this, I will get maximum at the neutral surface, and its variation I already know. Tau will be given by V shear stress. This V coming here at this section into Q is a factor divided by IB. Q is A into Y bar, A area of this section multiplied by the distance of the distance from the neutral plane. And we also know from the pure bending equation, for example, if it is flexure stress is coming Fx at this point, if it has any value Fx at this point, Fx is equal to m times y divided by the moment of inertia of the section. So here it will be shear stress like developing like this. So if we analyze this small section, we will see what are the stresses that will come on this. From this you will see that both normal stresses as well as shear stresses are coming. For example, normal stress I will draw like this. Fx is coming, I already show you now. Fx is coming like this, and shear is coming along all the planes, like this, like this, like this, and this one. So it's having the planes which is having shear stress and the flexural stress as well. So I can convert these planes from my analytical equations to those planes which are only having principal stresses. That is, the planes having no shear stresses. For example, I got those planes like this. My section turns like this, and I got the principal planes like this, such that it makes now the principal stress F1 is like this, F1, and let it be tensile force, and it will be F1 here, and this will be the another principal stress F2. It will be the compression one, FC. FC. It makes an angle alpha with this. If I see this point, these are the principal stresses coming on this small element that we take up from our beam section. So this is at one point. These normal stresses and shear stresses, normal tensile stresses and principal compressive stresses, if I make them to locate on all the points inside the beam, I will get some trajectories that will represent the principal stress trajectories. When I see those principal stress trajectories, those will be like this in my beam section. When I see this principal stress trajectories, for example, I took this block here. If I took another block like here, another one like this here, another one like this here in my beam section, I will get stress trajectories which will be having principal stresses only, not any shear stresses. So if I draw all those trajectories, I will first let me draw the principal. I will get trajectories like this. These are the principal stress trajectories. Like this one. If I take one element here on the trajectory, I will see that one stress trajectory is passing through it. It will have like this one here, point here. So this one, as I know, this is in compression zone, this is in tension zone. So the stress trajectory is within this compression zone. It will be dominated by the compressive stresses like this one. So when I come to this point, it will give a compressive force like this on this element, because it's a stress trajectory coming from the compression zone. Same is the tensile trajectory, another principal stress trajectory coming from the tensile zone. If I see this tensile zone, it will be doing fiber, acting on the fibers like this, trying to elongate them. So if I extend this trajectory like this, I will come to this point. I will see at this element, it will be, let me make it with different color. It will be making it to elongate like this. The same thing I showed on this point. This point is the same thing. This is compression coming like this from compression stress trajectory, and this is tension coming like this from the tension stress trajectory. So if I see that concrete is very good in compression, so I have not to do anything with that. But take this tensile forces that act on our small element. These tensile forces will try to create a crack like this, like this. Crack will be like this. It is stretching it like this. It will like it will try to get rupture like this from the middle one. So if I from these stress trajectories, if I want to draw the mm, possible pattern of the cracks in my beam, it would look like this. It would like look like this. The cracks would emerge like this. These are the cracks which got induced on our beam as a result of both flexural stresses as well as shear stresses. This is the potential profile of the cracks in our beam. So you got a idea about how our shear stresses in combination with flexural stresses are responsible for the cracking of our beam. So now to prevent these cracks, we design in addition to the tensile reinforcement that we provide for flexural stresses. For shear stresses, we provide shear reinforcement. Shear reinforcement, that shear reinforcement we provide it in the form of stirrups. For example, we have shear tensile reinforcement like this, compression reinforcement like this. We provide the stirrup reinforcement like this to give to give our beam section resistance against the shear. So here you got the brief idea about the stresses coming on our beam and why we require shear reinforcement. I'm sorry, there is a bit of disturbance from the outside. So we will come to the basic formulas that we will employ in our solving our problem, design problem. Please mute your mic. Everybody, please mute. So problem formulas that we will require. First, nominal shear stress. We know nominal shear stress that comes on our beam section is the shear force that is applied to the area of cross section, VU by BD. Now this is for those cross sections which are having uniform depth. If the depth of our cross section is varying, like we see in our cantilever beams, or like that arch type beams in our, there our depth varies as the with the span of the beam. So for those we have formulas for net shear force is equal to vu plus minus mu by d tan beta, where beta is this angle. Beta is this angle. These formulas you would have studied in the online lectures. It is, their derivation is in full detail in the lectures available. You can go through those lectures and see their derivation and their I mean to say that concepts behind them. Now we got our net shear force like this. We will divide it by the area of cross section at that point. BD is the area of cross section at that point where we want to know our, for example, this is our beam of varying depth. We have a shear force V acting here. Here, what will be the depth D at the section where we are calculating our shear stress? It will be VU net by BD, which is VU plus minus MU by D tan beta by BD. Now this negative sign we use here in this formula, negative sign at that time when mu bending moment increases as the depth increases. For example, in our cantilever beam projection, we will see here, here it is subject to point load P on the tip. So if we draw bending moment diagram for this point load, we will see bending moment diagram is increasing towards the support, and the depth is also increasing towards the support. So as bending moment increases, depth also increases. We will use our negative sign. Similarly, when we will use positive sign, if we see here, it is continuous like here. It would have been something arch type like here, but for this we will have a varying depth up to this section. So if we drop the bending moment diagram for this beam, like from this section to this section, we will have a bending moment variation like this. It is zero at this support end if we consider it to be simply supported, and it increases up to some loading. But we see that here the depth, here the bending moment increases, but the depth decreases. Depth decreases in this direction, bending moment increases in this direction. So we have to use the positive sign here for solving our examples. Another formula that we will be using, tau c max. Tau c max is the maximum shear strength of our concrete. It is given as 0.62 under root FCK. It only depends upon the grade of the concrete that we are using. It's the maximum shear stress that our concrete can resist without having any shear reinforcement. SV is the spacing of our stirrups. It is as per the code. We have to give the spacing to our stirrups as per these three conditions. We have to check all these three conditions, and the lesser one among the all three will decide what will be the efficient and economic spacing for our stirrups. Also, the formula for the shear stress that will be carried by our stirrups is tau v minus tau c into bd. Here, this term tau v is the nominal shear stress coming on our beam section. Nominal shear stress coming on our beam section, and tau c. Tau c is the shear stress taken by concrete. Or we can say that the shear strength of our concrete, or how much will be the shear strength of concrete. The shear stress taken by the concrete, or shear strength of our concrete, depends upon the percentage of the tensile reinforcement, PT. And this nominal shear stress is just like this, VU by BD, that I already told you. Nominal shear stress coming on our section. Nominal shear stress is called VU by BD. These are the some basic formulas that we will require in solving our numerical example on the design of the shear stirrup for our design problem. So let me go to the design problem. Yeah, we are given a beam section of width 250 mm, which is having an effective depth of 348 mm. 348 mm, and the Tensile reinforcement provided in our beam section is having total area of 1232 mm square. Okay, it is also provided, it's a W reinforcement beam, it's also provided with some ASC, and we don't require that value for the calculation of our shear stirrup specifications. So also the thing that is also given is the factored shear force that is coming on our beam section at a beam section, and this I am taking at the critical section 90.8 kilonewton. From the online lectures you would have already studied about what are the critical sections for the design of our design of shear stirrup. Let me give some brief idea about the critical section. For example, if you have a beam like this, uh, it is supported like this on column. So as per the it is having some effective depth D. As per code, we have to take the critical section for the design of our stirrups at a distance D from this. At a distance D from the sorry, at a distance D from the face of support. At a distance D, where D is the effective width. Effective depth of our beam section. This beam is subject to the same conditions and conditions. So we will be designing the shear steps for the critical section, which is at a distance D from face of support. There are other conditions. What will be the critical sections for other conditions? For that, I suggest to you to go through all the lectures that are given in the naphthalene side. You will have more insights into this. What are the critical sections for calculation of our shear forces? And for those critical sections, we have to design our shear stirrups, because within the critical sections, we will have more shear forces, which obviously leads to more shear stresses. And in those critical sections, we have to provide this less spacing of the shear stirrups to carry our critical shear stresses. Away from the critical sections, we can provide a bit larger spacing to the shear to the stirrups, or in some cases we don't need to provide the shear stirrups in the sections where we don't have that much shear forces, which will be beyond the shear strength of concrete. So for that, you should go through the lectures to see all these minute details about the critical sections where we need to calculate. So I am saying that we are having a factored shear force coming as 90.8 kilonewton, and that too at critical section. Critical section. So nominal shear stress. First thing that we have to calculate is nominal shear stress. Nominal shear stress that will be coming. That is tau B is equal to VU by BD. I already told you nominal shear stress for a beam of constant depth will be VU by BD. We are having VU as 90.8 10 power 3 Newton. We are having our B as 250 mm, and we are having our depth D as 348. Yes, 348 mm. Newton divided by mm square is equal to megapascal. So it will, if we will calculate this one, we will get 1.044 ampere. Okay. Second thing is we have to calculate maximum shear strength. Maximum shear strength of concrete. Okay, tau C max. That is 0.62 under root FCK. That I already told you. It's 0.62 under root 25 FCK 25. It will come up 3.1 megapascal. Here you are seeing that tau V is less than tau c max. So our section is adequate. We don't have to redesign our section. This is one of the first things that you have to check, in your design process, whether our nominal shear stress is less than the maximum shear strength of the concrete. If this is the case, then you can proceed with the same cross section given. If this is not the case, your nominal shear stresses are coming greater than the maximum shear strength of concrete, you have to redesign your section. You have to provide different FCK or different dimensions so as to reduce the shear stresses in your beam section. Best way will be increasing the depth, because depth you will increase, your shear nominal shear stress coming on the section will decrease. And another thing, you can increase the FCK. From FCK your tau c max will increase. This is the first thing. Now AST coming. That AST that is being provided there is 1232 mm square. This step is a calculation of shear strength of concrete, AST. So PT, what will be the PT? It is AST BD into 100. It is 1232 divided by 250 into 348 into 100. When we calculate this PT percentage of tensile reinforcement, it comes out to be 1.416. This percentage of tensile reinforcement corresponding to this percentage and corresponding to FCK equal to 25. We have to look into code and find the shear strength of the concrete. In code there is a table given like this. It is given PT are given along these columns, this column, and it is given for the different shear characteristics concrete strength or concrete yields. So what value we were getting? We are getting 1.416. So where is our value lying? It is 1.416 lying here. 1.416. And what is our concrete grade? Concrete grade is 25. So first we have to look for this line. We got this line. And our concrete grade is 25. We got this line. So our value will be staying like somewhere between 725.725 to 0.742. It will be approximately closer to 0.725 because it is 1.41.6. So when we interpolate the values between these two things, we will get our tau CS corresponding to this table 0.728 megapascal. Clearly you can see that tau C is less than nominal shear stress tau V. So need for shear reinforcement. What does it mean that the shear stresses coming on our section, coming on our beam at the critical section is greater than the shear strength of concrete? That is, if we keep our beam section without the stirrups, it is likely to have cracks because the concrete is not fully able to resist the full shear stresses coming due to the loads at the critical section. So in order to prevent this, we need to design a shear reinforcement for this critical section. Now design of vertical stirrups step. Now next step is design. Design of our vertical stirrups. VUS. I already wrote a formula here. VUS, this is the shear stress carried by our stirrups. So VUS, it will be actually the total VU coming at our critical section minus the shear force carried by concrete, or we can say that tau C. VC, and VU is tau V into VD minus tau C into VD. It will be equal to tau V minus tau C into VD. Substituting, we are having all the values of tau V, tau C, B, and D. When we substitute all these values tau V is equal to 1.019 minus tau C that we calculated 0.728 megapascal, and BD is our 250, and our D is 348 mm. When we calculate the shear that is coming on our stirrups, VUS is equal to 72 point. We will do it like this. We will transpose this, because in our equations we will directly require VUS by D. So no need to multiply by D here again. Effective depth. So we will be getting, because why I am saying VUS by D, because here in the formula I am directly requiring VUS by D. VUS by D, this for the spacing design. VUS by D is equal to 72.75 Newton per mm. Thus, this amount of shear force will be carried by our shear stirrups. So I have to design shear stirrups for this. From this, we will assume we are using two-legged closed stirrups, or of 8 mm diameter. So if we calculate ASV represents the area of stirrups. ASV is 2 into 5 by 4 into 8 square. Actually, our stirrups are like this. These are two-legged stirrups. So we have to take the area of this one and this one. These are two. If it would have been more like this, because the stirrups will provide like this stirrups also, like this also. Here they become 1, 2, 3, 4, 5, 6, 6 left. So we would have to multiply by 6. Since it's two-legged stirrup, we will multiply by 2. It comes out to be 100.6 mm square. We are just giving an initial guess that we will use this stirrups that is providing a shear stirrup area of 100.6 mm square. So let's check the different things from this ASV. So if we provided ASV as that one, so the required spacing that we will be requiring, SV should be less or equal to 0.87 FY ASV by VUS by D. That's why I calculated initially US by D. I required this thing. You will get all these formulas in the lecture. These are discussed in detail there. 0.87 FI 415. I am assuming FE 415 for my stirrups. 415 into 100.6 divided by 72.75. This comes out to be 499 mm. This is the spacing required as per the area that I gave. Now let me check what are the code requirements. What code says me you have to place how much space. So code requirement, check in code requirements. Code says that your spacing SV should be one of these three cases: 2.175 FY ASV by D, ASY by B, This is first, or it is 0.75D, or it is 300 mm, lesser of any one. And when I plug all the values here, 2.175, 415, 100.6, these all are values we are having, Fy, Asy, B divided by 250. When I calculate this value, this comes out to be 363 mm. 0.75D comes out to be 0.75 into 348. Comes out to be 261 mm. And our this is 300 mm. Okay, we have to provide lesser of the three. So required was the area of stirrups that we gave ASV. From that requirement, we were having 499. What this suggests is that we were having 500, approximately 500 mm distance we can provide between the stirrups. But when we checked it with the code said that you have to provide stirrups even more closer based on the steel grade of steel you use it, and you based on the area of the stirrups that you provided. From that we got 363 from one condition, 0.75D was another condition, and 300. We have to provide lesser of all the threes, lesser of the three. So the deciding criteria will be 261. So to be on the safer side, we will reduce this one to furthermore. We will say, because we have to report everything in the multiplies of 25. We will say that from the design point of view, we will say that we will provide 8 mm diameter, two-legged closed stirrups at 250 mm center to center spacing. This is the required spacing of our stirrups, and the area that we provided is we provided 8 mm two-legged stirrup. So this completes our design problem for the design of stirrups for given shear force coming on the critical section. So we can then have this one. I guess we can draw a detailing like this as well. This was our beam section. And it was supported on this side like this one. It is some column or something coming at this time. It was coming at this distance was our 348, and this distance, this longitudinal reinforcement coming. I will draw it with a different color. Longitudinal reinforcement coming like this one. This was our longitudinal reinforcement coming, and this was our compression reinforcement there. So we designed our stirrups at this critical section. This one. So we provided a stirrups of two-legged stirrups like this. Stirrups. We will also provide stirrups here, but we will increase the spacing as this is not our critical section on this side. Provided. Here we have to provide these stirrups at uniform spacing close to each other. So if if I write provided these provide this 8 mm 5 to length at the rate of 250 mm center to center. So my this there will be continuous from this side. We can also make this continuous from this side, and my cross section would this from the side. My cross section would look like this. Like this, and provided stirrups like this. I have to make these closed ones. These are closed stirrups like this. Here we have to make the bands like these, 135 degrees. These are the details that you will study in detail in the classes. I have to make this 135 degrees. So this was our coming as 250 mm, and this was coming as 400 mm. Sorry, 348 mm. This is the basics of the design of the shear reinforcement for our beams at the critical section. You can solve any problems by following these steps. Steps are very simple. First, you have to locate the critical section. After location of the critical section, you have to note down the factor shear force coming on the critical section. Since in the problem that I discussed here, shear force was already given. Like this one, shear force was already given 90.8 kilonewton. But in the design problems that you will get in exam, you will be given the dead load, the live load, and the self weight of the beam. From those things, you will calculate the total loading coming on the beam, including the self weight as well. Then you can draw the shear envelopes. From those shear envelopes, you will get the shear force at the critical section. Shear envelopes are just the shear force diagrams you will draw, and then at the critical sections you will note down the ordinate of the shear force diagram and get that. I mean to say that factor shear force. From factor shear force, your first step is calculation of normal shear stress. Second thing is the checking of your section whether it is adequate or not. That is by calculating the maximum shear strength of the concrete. If the maximum shear strength of the concrete is greater than the nominal shear stress, then you will proceed with that section because the section is adequate enough. If that doesn't happen, you will need to redesign or revise the section dimensions. So when you pass this step, next step is calculating the shear strength of the concrete. When you calculate the shear strength of the concrete, if the shear strength of the concrete comes less than the nominal shear coming at that critical section, you will have to design shear reinforcement for that section. Once you got this clear indication that you need shear reinforcement at the critical section, then you will proceed by these formulas, calculating the shear force taken by our shear stirrups like this. Then you will assume two-legged shear stirrup or three-legged or four-legged based on the specifications given there. And after that, you will perform the checks for the spacing of this stirrups. When you perform the checks based on one formula like this spacing, when you assume the area of the shear stirrups, and checking the code requirements as well. Among all the three, you will provide the minimum one, and that will be also the multiple of 25. And then you will show the detailing at the critical section like this. This is all for this design of shear stirrups for beam. Thank you so much. This is all for today. Thank you so much everyone for joining this session. Hope this was helpful for you.